So a worked example using Newton's law of gravitation. In this example we're looking at the force between the moon and the earth. So listing our variables and all these kind of things like the mass of planets, the radius of planets is given to you in data sheets. But the formula is F equals G m1 m2 over r squared, and we can substitute that in to get the gravitational force acting on the moon due to the earth. And to two significant figures, that's 2.0 times 10 to the 20 newtons. And then it asks us about on the earth due to the moon. Now, quite simply then, by Newton's third law, the magnitude would be the same, but the direction would be the opposite. Okay? But it also follows because if you substituted all the numbers in, you would get the exact same value. Another example, calculate the gravitational force between two protons in the nucleus and take their separation as 1 femtometre, so 10 to the minus 15 metres. And there you get the force is 1.9 times 10 to the minus 34 newtons, so it's tiny. Even in that very close range, right, very small value of r, because the masses are so small, the forces are very small. Gravitational forces are not significant within the nucleus. In later units we'll see that the strong nuclear force is the force that keeps the nucleus together.